file of the lectures today using this link. Hope if you've not done it, maybe wait a few minutes that you've done it. You do it? Okay. So the plan of the lecture for today is somehow to explain the main properties of the NV centers in diamond in a nutshell. This is so the NV center in diamond is an atomic-like quantum system with discrete levels inside the diamond gap, and we will try to see how this comes from. And the ground state of the electronic spin is a spin s equal 1 for the negatively charged NV center. And we can describe the system by this Hamiltonian, which is written here. Okay, so if we first consider this term, the first term here, you see that if I write it in the basis of the state ms equal 0 and plus minus 1, this will be, we will have then this structure. The ms equals 0 will be the ground state here, and separated by this parameter d here, we will have, this is d actually, here, we will have the two degenerate state ms equal plus minus 1. Okay? And what does this mean? This means that then we can certainly now change. We have this difference, this frequency between the different states. And what's important is that now, if we apply it if we add now the coupling to a B field, there will be a Zeeman effect. Same as previously, it will modify the structure of those Zeeman. So somehow it will remove the degeneracy of those states by here ms equal plus 1, and here, for instance, ms equal minus 1. So this is an important point. But then there are two important features, and we'll try to explain them. The first one is that we will be able to polarize the population efficiently in ms equals 0 just by optical mean. Applying green laser will automatically polarize the light into ms equals 0 state. And at the same time, so we can discriminate the two levels simply by looking at the intensity of their respective of the associated luminescence coming from them. And that's also an important feature that we will try to understand. So we have the state discrimination that is possible. And so the main properties after that is that we will be able to drive by magnetic resonance transition between those states, for instance, going from ms0 to ms plus 1 or to ms equal 1 plus 1. And then by observing the difference of the resonance frequency, we can use the NV center as a magnetic sensor. That's the first properties. So then there are all the sensing properties of the NV. Comes from basically this Hamiltonian. We have a zero field coupling, D, the D parameter, can be modified by temperature, strain, everything acting on the crystal. So we will see that in different experiments. The Zeeman coupling, the frequency difference between those states is about 56 megahertz per millitesla. So if you apply a magnetic field of about a few millitesla, you will be easily able to detect it. And that led already to a myriad of applications. And then also something important is that there is this term that we see here, this important term there, which is that describes the hyperfine interaction, the coupling between the spin S and the nuclear spin. So somehow this will using this property, we will be able to use the NV center to couple to nuclear spins. And those nuclear spins can be either within the diamond, and we've seen yesterday that there are basically two possibilities: nitrogen atoms that has a spin either 1 or 1/2 depending on the isotope, or carbon-13 that has spin 1/2, nucleus spin 1/2. And we'll try to see how does this matters, both for good means, as a useful resource somehow, but also as a drawback somehow on the system, because it is, for instance, the interaction with the nucleus spin of carbon-13 that will set the limit of the T2 time that we've seen for the coherence of the spin state. Okay, so all this somehow is a program of today. The program of today is to understand the level structure step by step, and after that to describe how, for instance, how we can polarize optically the system into that state, and how we can discriminate those two states, and how we can drive them using magnetic resonance technique. Okay, so NV magnetometry, for instance, if we take the main application of NV centers, it is for using them as magnetometers. So the discovery of the quantum properties of the NV centers, where the first paper was done by Jörg Wartop here, and that was published in 1997. And then that was a beautiful result, where basically they were able to observe single NV centers dispersed in the diamond crystals, and drive their spin resonance and detect them optically. So it's the first paper in which the very important properties of the NV were directly highlighted. You can detect them at individual level first. You can, they are photostable at room temperature, which is a remarkable property. At least this was the only system having that feature at that time, this perfect photostability at room temperature. And then you can drive them for magnetic resonance. They have a spin structure, and you can detect the magnetic resonance in the spin manifold by optical means. So these three important main features of the NV were discovered at that time. Then it took 10 years for people to realize that somehow the magnetic dependence of the NV center spin manifold can be used as an optical magnetometer. And there were two papers published on one side by Jörg Wartop and Fedor Zhelezko, and the other side by Misha Lukin, Dima Butker, and Phil Hammer, which highlighted this main feature. And so now these event products about that. So you have here a system that was shown, a demonstrator that was shown at the Salon du Bourget in Paris. And Salon du Bourget, it's a very important aerospace event that occurs every year in July. And Bosch showed that a very compact system in which you have a diamond crystal. The diamond crystal is somewhere there, somehow. You see it here. So that's the diamond crystal here. And then everything for the microwave resonance, for the detection for that, is done within a red pitaya system, so that you have everything on a chip, which is that dimension typically. It's that kind of thing. So the dimension of the chip, of the full chip, is around like that. And there are nevertheless still some batteries that are needed so that you can have portable systems. So again, it's a nice illustration of what I said yesterday as a conclusion. It takes 20 years to get from pioneering work to mature industrial application. You see, 20 years, almost the time between the publication of this paper and first demonstrator that are somehow can be put on the market. Okay, so the organization of today's lecture: why diamond? What is a crystal? What is the specificity of this crystal? Why are impurities in diamonds so important, and why they have been studied so extensively in the past? And what's the specificity among those impurities of the NV centers? Then if I want now to describe for a more physical point of view a point defect in the solid state, I need to understand how this can be done. And I want to make a kind of parenthesis. I will not, since the NV center is rather complicated to describe, I will use a much simpler system, which is also the F center in alkali halide. And that will give us a toy model to describe very important topic, which are we will obtain the energy levels, we will illustrate the Jahn-Teller effect, and we will also be able to describe the main properties of luminescence, what is the zero phonon line, and what are the phonon sidebands. And then we will apply that general ideas somehow to the NV centers. We'll construct the electronic wave function associated to the symmetry of the point defect within the crystal. Then that will be able, so that we'll able to have the electronic spin state, construct the ground state Hamiltonian, and explain why we can detect optically magnetic resonance. I think I will need all lectures for today to achieve that plan. And of course, as before, do not hesitate to ask questions if something is not so clear. So, okay, perhaps historical point of view. Let's start with diamond. Diamond is, of course, very well known for a long, long time. But the first demonstration, the first interest in diamond from scientific point of view is actually the work of Lavoisier. And Antoine Lavoisier was doing a chemist and was a chemist in France before French Revolution. And actually was working closely with his wife, Marianne, and you have beautiful portrait painting of them by a famous French painter of that time, Jacques Louis David, where you see the two persons experimenting. And after Lavoisier was guillotined during the French Revolution, and his wife, after that, published all his scientific work. So you have all the scientific work on that. And there is one work about the destruction of diamond by fire. And so how the story is told is that using a magnifying glass, Lavoisier focused the sun's rays on a diamond placed under a glass bell. And after that, using the influence of solar energy, so the diamond gets consumed, is completely consumed, and then using the residual gas that were released by the fire, then he could evidence that these gas were carbon dioxide. And so basically, it indicated that was a proof that the only element in diamond was actually carbon, at least to the possibility of that time. And so you may ask yourself, what was this magnifying glass, which is a kind of something that you can purchase. Actually, this is this system. So it was a giant lens that was commissioned by the French Academy of Science, and you see how it worked. So you could collect using this huge lens here and the focusing lens here, all the light coming from the sun, and focuses onto a furnace here, where you could reach very, very high temperature, and you could even see Lavoisier experimenting, and he was taking care about safety issues by wearing some appropriate glass. Okay, and that's and that tells us also that Lavoisier was a very powerful man at that time. He was actually collecting taxes for the king, and could have that kind of I could ask the French manufacturer of glass, Saint-Gobain, to produce that, which was a huge effort to make this kind of system at that time. So we have the same element, carbon, but in two different compounds. We have, for instance, coal here, and we have diamond. And obviously, they are not the same structure. And you all know that somehow coal or graphite has this plain structure with sp2 bonding, and that leads to graphene, for instance, if you can you can extract 2D materials from that. And diamond have sp3 bonding with covalent bonds with really tight system, which gives all the important properties of bulk diamond. And the difference of structure was actually found by Bragg in 1913, just after the invention of X-ray diffraction. So Bragg used that and could identify the crystal structure by by electron diffraction in the at the very in early 20th century. So, of course, what was also very important was to be able to produce diamond and to have man-made diamond. And that was a huge effort after the Second World War, because not for gem, actually, but people realized that it was very important to have very hard materials for polishing for a metal industry. So this is really to have cutting tools, to have all that. And so, of course, you want to have the hardest material, and the hardest material for that is diamond. So, there was a really lot of money in the US and elsewhere that was put on the development of ultra-hard materials, and especially targeting the synthesis of diamond. The first success came from Sweden, by a company, SiC, in 1953. And that was a technique where basically that was here. It was a sphere that was in which they put some materials, like two hemispheres, bounded close to each other, and after they could apply, by this press here that you see, huge force on that. And they could achieve a very high temperature by these kind of electrical suppliers that you see here. The temperature was 400 degrees, and pressure was about 8 GPa. And they could have some very tiny diamonds appearing after this process. But that was kept completely secret. And the reason that was explained by the leader of the team that you see here, Lundblad, was that he said, we thought we had a lot of time. So they wanted to refine their experiment to produce more diamonds, bigger diamonds, et cetera, et cetera. But at the same time, there were competing teams in the US in General Electric, and you see here one of their press in which they were able to grow diamond, following a little bit the same technique, but the press at General Electric was much more reliable than the other one, which was very difficult to handle and somehow very dangerous also to what they say. So the first experiment was realized in December 1954, and it was publicly announced as a press release in February 2 months later. The first diamonds were commercialized by General Electric in 1957, but the HPHT synthesis was reproduced by De Beers in 1959, and there's a nice story about that. So this is typical now how we do HPHT synthesis of diamond. So you have here this type of press. Basically, the idea is to reproduce the condition that you found in the Earth, for which diamond is stable, is thermodynamically stable. That means a very high temperature, around 1,500 degrees Celsius, and high pressure up to 5 to 7 gigapascal. And that is obtained using this big tank. And what you do is that you need to introduce both solvent and catalysis inside the material. So we have impurities to somehow enhance the growth rates, otherwise the growth wouldn't start. So to start the growth, you need to put iron and nickel and other things in the product, in the starting product, and after you compress them at high temperature and very high pressure. And then after that, you have typically those kind of diamond, which, and I will explain their color. They are not perfectly transparent. They are somehow yellow, and I will explain where it comes from. And you can have also those kind of giant press in laboratories. There are only a few laboratories that in the world that can do that. For instance, this is a press in Japan at Nirim Institute where they do that. It's another kind of different. They are very different. They are a series of different geometries for those press. What was also important is that the research that was done at General Electric was under US secrecy. So it was, they had by the government funded that research, but said you must keep them secret. And after a while, they realized that they had competitors. So they said, no, we should patent it. And then they patented it in August 60. So, and De Beers patented, was able actually to reproduce the synthesis completely independently. They knew somehow what you had to do. So once you know that that is a good way to follow, of course, you do it much quicker than the one that do the first thing, that are the pioneers. And they patented only 1 week later. And then there was a fierce battle of advocates, between advocates of the two companies, on what is a definition of a solvent and a catalyst. So in one patent, they say it's a solvent, and in another patent, they say it's a catalyst. And so they argue about what's the difference. And at the end, they came to a financial agreement. So General Electric had the patent, and then De Beers paid for license, got the right to the licensing right, and for a while the amount that De Beers paid to General Electric was also secret. It was around a few $billions at that time. Typically, what you produce, the amount produced in the world is about, mostly by element 6, is around 800 tons per year. And basically, it's done for industry and mostly for abrasive. So what you would do, for instance, is to crush those diamonds into tiny particles, micrometer size or even below, and then use them to integrate it, for instance, in cutting tool, drilling machine, all those kind of things. So it's really important, and you can purchase, diamond blade knife for cutting in your kitchen or those kind of things. But really, there's a very important market for those kind of products. Okay, so if we start from that, let's try to understand the yellow color. So the yellow color is associated to a diamond classification that came in the 30s, that was proposed in the 30s by Robertson, Fox, and Davis, who was mostly geologist at Imperial College. And Imperial College has a beautiful gem collection, mostly coming from India, as you may imagine. And they use that resource to test, to do spectroscopy on all diamonds. And basically, they did systematic infrared measurements of infrared absorption measurements. And then they found that basically there were two big categories, two main categories. And that they gave different names. Type 1 diamond exhibit a strong absorption band at a wavelength of around 1/8 micrometer, and that is also associated to the yellow color I showed you before. And type 2 diamond, there is this infrared band does not appear at all. It's perfectly transparent in the infrared, and also perfectly transparent at highs. And that will remain completely unexplained. There was work, there was even people that thought that there might be two different types of diamond. Also, they had the same crystallographic structure. There might be subtleties that explain the different things. And actually, it was Kaiser and Bond at Bell Labs who found the explanation at the end of the 50s. Kaiser and Bond, it was the development. Bell Labs was certainly the most important lab in the world at that time, at least for condensed matter. And they were assigned the task to measure impurities in semiconductors, especially for silicon. That was the development of transistors, so it was very important to have ultra-pure silicon or germanium or all these semiconductor crystals. And for that, they developed very accurate mass spectrometer. And the idea was simply, you take a piece of silicon, for instance, you burn it, and then with your mass spectrometer, you analyze all the elements that are released. That give you the amount of impurity in your sample. And they could show like that the main impurity in silicon is actually oxygen. So they had the idea to use this and that was somehow a key result for the birth of the semiconductor industry, because after that, they put huge efforts on the purification techniques of silicon and to get larger and larger ultra-pure silicon wafer. That they decided to apply the technique to diamond, the same technique. So somehow it's reproducing the Lavoisier experiment, but now being able to analyze the content of the gas that are released by the destruction of the diamond. And then they identified that the infrared absorption at 8 micrometer was linked to nitrogen. And they could even measure that very accurately. So this is their result. You see here the nitrogen concentration in percent, and you see here the absorption coefficient measured in the 5 different samples that you have here of diamond, from something very pure, almost zero in diamond, so that would be a type 2 diamond, almost a type 2 diamond, and that would be a type 1 diamond with a very yellow, with this yellow, specific yellow color. And then they found that the absorption here correspond to a concentration of about 0.3, 0.2, 0.3% of nitrogen. So it means that typically the nitrogen concentration is around 100 ppm, part per million. So it means that somehow you have 1/10 to the 4 atoms of the diamond crystals that are actually nitrogen. Nitrogen is just 1 electron plus the carbon atom. So you see that it can be integrated very easily in the diamond lattice. And we come back to that, of course, for the NV centers. Okay, so now you can ask yourself, okay, I have this huge amount of nitrogen in the crystal, in type 1 crystals. How are they integrated? And somehow, again, oh, sorry, let me see one thing. Okay. Yes, I will come back to that. Yes, sorry. So how you can also produce ultra-pure diamond? So you can imagine that the HPHT process is very difficult to do in a closed environment, of course. So there is another approach that has been remarkably successful for growing diamond. This is the plasma-assisted growth of diamond. So basically, it's a different approach. In the HPHT synthesis, you want to reproduce to be in the domain where diamond is thermodynamically stable. So somehow you have to be at high pressure, high temperature. The other approach is not. You are in vacuum, but then you know that diamond, for instance, can be metastable. So somehow you will be in a process under vacuum where basically you create the sp3 bonding will be more favorable by kinetics compared to sp2 bonding. And that you can create layer by layer sp3 bonded layer of atoms like that. And at the end, you get a beautiful diamond crystals. And basically, for doing that, you have a plasma here. And the plasma, you inject in the plasma that is created by strong microwave excitation. You inject both methane and hydrogen atoms, hydrogen gas. Those methane and hydrogen gas will dissociate. And using a process that there is a cartoon movie that tried to explain that, at the end, you will deposit layer by layer the carbon atom and create like that a crystal. So to get a layer of about 100 micrometer width, that would require a few days of this CVD works, of this CVD growth. And you can, of course, for doing that, you have different possibilities. You can do what is called a homoepitaxial growth. So you can start here with a substrate, but you need very good crystalline quality. That purity is not important. That can be, for instance, a very good crystal coming from HPHT synthesis, and actually it's what people do. So that will be the seed, and you deposit on top of it the layer. But that layer can be ultra pure. And at the end, you cut that layer, you retrieve your seed diamond that can be reused for a few times, and then you, using that ultra pure layer, then you shape the diamond as you want. And of course now, this has been a technique that especially here in India and in China, where there are huge plans now to create diamond for gem using that approach. And the price of diamond gems has dropped off due to the event, the diffusion of this CVD growth technique. And this is, for instance, a machine. You can even try to do it in your garage. You need just a big power supply, electric power supply, and some air cooling and some gas to do that. And basically, you feed them here, and it's a SiC. This is produced by SiC, and there are many, many other companies that can produce this. SiC is perhaps the best one if you want to do diamond for scientific purposes. And this is how it works. If we see it here, I hope it's going. So this is coming from L06. And you see in this cartoon, so that's the hydrogen atoms here. And you see here some methane molecules that have been dissociated. So one hydrogen has been released. And from time to time, you know, these carbon atoms stick to each other. And there is pending bonds here, and another hydrogen carbon atoms can come, and step by step, like that, you create the diamond layer. That's somehow the idea. Okay, so, and using that, you can you can grow those electronic grade diamond. For instance, that was developed and installed level by Element 6. Electronic grade means that now the nitrogen content is below the part per billion. So much, much lower compared to anything that can be realized using HPHT or the other technique. And you can even do some doping. I will show you how. And there are a lot of companies now that can produce that. iQute is a French company that was started a few years ago to produce and to release those kind of diamond. And typically, a 3 by 3 millimeter slab and 200 micrometer thick electronic grade diamond would cost around 2,000 euros. You can even purchase that from Thorlabs now. Okay, the important point is that with this technique, you can dope CVD. You can have doping. And of course, as you know, diamond is a wide bandgap material, 5 electron volts for the energy difference between the valence band and the conduction band. And that means also that diamond has this unique property to be transparent over a very large electromagnetic spectra, going from the X-ray to the infrared, to the far infrared. So nevertheless, you can integrate defects in the lattice, such as vacancies or impurities that come in substitution to a carbon atom of the sp3 lattice. And the name is that will change the color of the diamond. So that's why, that's why we call them color center. And for instance, if I take, for instance, boron will set an acceptor here, acceptor level here, and there can be transition between the valence band and these acceptor levels, and those boron doped diamond then exhibit a very nice blue color, and there is this beautiful gem that is now at the Smithsonian Institution in New York, which is called the Hope Diamond, and there's a very nice story about that. The Hope Diamond came from India, was purchased by a French guy and for the French King Louis XIV. During the French Revolution, all those gems from the French kings were stolen at one point. Part of them were retrieved, but the Hope Diamond was never retrieved, was never found. And then there were stories about it. It was certainly recut somewhere, and then purchased by different people, and at the end was purchased by someone named Hope, and that's where the name comes from, and you can see it, and it's really amazing. The color is really fascinating, and it's not very big, but the color is very impressive. Okay, now we come back to science, and we look to the nitrogen inclusion. If we take, for instance, sample about 100 parts per million in the sample, how are those impurities organized? And again, it brings us to the lectures of yesterday. There were people at IBM who decided to use electron spin resonance spectroscopy. And so they wanted to measure the signal associated to nitrogen. So they say, okay, my lattice, I will have nitrogen impurities. Those nitrogen impurities will have either will have a electron spin of 1/2 due to the electron coming by the left, not bounded by the other carbon atoms, because it's now in substitution. And we should see a signal coming from this single electron associated to the nitrogen. But then they found that if they compare the strength of the electron spin resonance signal, actually it was much weaker to what was expected. And they say that they showed that most of the nitrogen atoms actually exist, for instance, as pairs of nitrogen atoms or clusters of nitrogen atoms, so that somehow these complex systems do not have do not contribute to the signal, to the electron spin resonance signal anymore. And then it was found by Gordon Davis and other people in the 70s that actually they do very thorough, very complex spectroscopy and work to understand all these defects, as evidenced by specific optical absorption, specific luminescence measurement associated to that. And then they demonstrated that the properties of all these defects can be modified by high energy irradiation, electron irradiation with mega electron volt energy. These electron irradiation will create a lot of vacancies in the crystal. This is well known from particle physics, from nuclear physics. And after that, using thermal treatment, you will move the vacancies. They can remain as dispersed vacancy, but they can also bound to impurities in the crystal and then create complex color centers, giving rise to different colors. And this is just an illustration of that. You have here microcrystals. This is a microcrystal here of about 100 micrometer. And we start just by looking at it both in white light and the luminescence under green laser excitation. And basically, you see just about approximately nothing. If we go now, for instance, to an electron beam facility and irradiate the crystals with high energy electrons, this will create a lot of vacancies. And then at the end, a green color appears. So you can see that it's greener. There is a higher green color compared to the one that was already existing a little before, but now it's more intense and more uniform. And at the same time, if we excite the luminescence by green laser, we see some red light starting to appear. But what you can do after that is anneal the sample at temperature around 1,000 degrees for a few hours. The vacancies will diffuse, and at the end, you see now somehow you change the color. The crystals appear like with a very nice pink color that you can see by eye. And now, if you excite the crystals, if you put green laser light on top of it, you see a very bright red luminescence coming from it. And actually, what you have done here is the creation step of nitrogen vacancy centers. You start by samples that have a lot of nitrogen. That's why they have this yellow color at the beginning to start. The irradiation will create vacancies. Those vacancies become predominant. That sets the green color at bare eyes. But this is not yet the NV centers. vacancies and nitrogen impurities are not bounded together. During the annealing process, the vacancies will diffuse and then will meet somehow their partners, bound with a nitrogen impurity to create the NV centers, and the luminescence will come from the system, and that's also associated to this pink color of the crystal when you see it by eye. And that will be, again, the kind of recipe that we're going to use to engineer the NV centers in the material. And, but again, if I come back to the 70s, it was not very clear to what was the reason for that systems. But then, again, Davis and Hammer at King's College in London found that it was associated to a very bright luminescence with a specific wavelength at 637 nanometer. And this is exactly the NV center zero phonon line that we will try to explain. So somehow this was the first paper where the NV centers was somehow identified, of course, in an ensemble. So the NV center can exist in different charge states. If you take now a nitrogen, so the NV centers will be the combination, the association, the bounding of a nitrogen impurity occurring, taking place, removing a carbon atom and taking its place in the lattice, and bounded with a nearby vacancy. This is one carbon that has been removed from the lattice, so there is a vacancy. Now, if you count the number of electrons, how many electrons you have? You have, from the associated to the vacancy, you have now 4 bounding structures. Okay, so you have 3 electrons that comes from the different carbon atoms that are associated to the vacancy, that are close to the vacancy. And then there is 1 electron coming from the nitrogen, similarly to the carbon atom. But at the same time, you have, since nitrogen has 7 electrons and carbon 6, you have an extra electron coming. So in totals here, I have 5 electrons. It's a 5-electronic structure, 5-electron structure. And that gives rise to a specific spectrum that you see here with a zero phonon line here you can observe in crystals. So this somehow is the identification, it's the mark, the signature that you have this NV0 crystal that is at 575 nanometer. Okay, and now if we add 1 more electron to the system, to get 1 more electron, for instance, you can have another nitrogen atom nearby, acting then as a donor, so it will give an electron, a supplementary electron to the system, and then you have now 6 electrons here in this structure, and these 6 electrons will create the negatively charged state that you have here, and there is a shift of the luminescence associated to the new charge state, and the zero phonon line that you see here, which is at lambda, again, it's a zero phonon line at 637 nanometer, which is exactly corresponds to 1.99405 electron volts. Okay, 945 electron volts. So this was a line that was observed, reported, and studied in the paper I showed before. So now our goal is to try to understand what is really the structure of this defect and why it gives rise to these properties and to this luminescence with this very specific feature, the zero phonon line, and a broad emission at higher wavelengths. And so the basic properties of the NV centers, most of the seminal contribution, the pioneering work was done by Jörg Wartrup in Stuttgart and Fedor Zelesko, working with him at that time, and now professor in Ulm. And basically, they investigated these envy centers. When the envy centers exist in a large concentration, it gives to the diamond a very nice pink color, as you see here. So this is another famous diamond that you can see at the Louvre Museum, which is named the Diamant Hortensia diamond. And also it belonged to Louis XIV, coming again from India, purchased by Louis XIV, stolen during French Revolution, but at that time it was refound, so not lost somewhere. And then Napoleon used it and gave it to the daughter of his wife, Josephine, and the daughter of his wife was Hortensia, the name. So, and maybe you've seen the movie about Napoleon by Ridley Scott. So it's the daughter of Josephine, and she used it during the coronation of Napoleon on the crown, and that was somehow, and you can see it now in the museum. So what's important, we forget all these kind of stories. They are nice, but not so important. But those defects really behave as artificial atoms. And it's really the main point that I would want to highlight. And again, the envy centers has perfectly stable luminescence at room temperature. And that leads to efficient and practical single photon source. And there were beautiful work, pioneering work done by Philippe Grangier in Saclay, and Kurt Ziffer and Weinfurter in Munich, just only a few years after it was the envy center was discovered, and then it has also an electron spin, as we will see, in the ground state that can be optically detected and manipulated by the combination of microwave and optical detection, following the techniques that we discussed yesterday. Okay, and you see here, single envy center dispersed in a crystal, and this is a setup that we developed with Philippe Grangier a few years later after this paper, where basically you have a green laser that was used here on shining light onto the crystal of diamond here, and we get the photons, single photons from the system, and we use these photons for doing a set of experiments based on using single photons. First, we demonstrated, we built a practical quantum cryptography testbed in which we encoded the polarization on the photon emission on each single photon produced by the envy centers. So that was just the implementation of the Bennett-Brassard BB84 quantum cryptography system. Then we did a few experiments where we reproduced single photon interference together with Philippe Grangier and Alain Aspect, and we realized what's called the delay choice experiment. And the delay choice experiment is an experiment where you ask yourself, where you try to push the question of wave-particle duality up to a given limit, and you ask to the photon, are you either a particle or a wave after somehow it has done its travel, following the quotation by Wheeler. So if you want, if we have time, I can show you that experiment. I liked it a lot. We enjoyed it. We enjoyed the realization of that experiment, really. Okay, but it's a little bit far from the main purpose of those lectures. So now we come back to really after this rather long introduction, the description of a point defect in the solid state.
Can we take a small break?
Yeah, sure. If you have any question on that, well, it was mainly no. Okay, then we can continue. Okay, so we describe now the point defect. And for that, we will change of system because we'll see. The description of the envy centers is rather complicated and technical. So to get the main message, I would go to a much simpler system. And the much simpler system is what's called the F center in alkali halide. But most important is to understand how we will model this point defect. And that has been not so easy to find. It's actually the contribution of Sir Neville Mott. If you take a perfect crystal, you have this translational symmetry, and you learn in solid-state physics course that somehow you have to build a wave function of the electron that is compatible with this translational symmetry. And what you say is that the electron moves in an average field, in a mean field that is created by the nuclei of the lattice and the other electrons. And this motion of the electron is associated to a delocalized wave function, and that respect the translational symmetry of the crystal, and this is the block state, again delocalized on the whole crystal. And so people understand that very quickly. At the end of the 20s, it was a thesis work of Felix Bloch under the supervision of Heisenberg to build this kind of formalism and then to understand how the organization, the construction of this wave function, of this block function, depending on the symmetry of the crystal, and associated to the Fermi surface. Okay, so this is a standard solid-state physics you learn. But if you look now to a defect, it's completely different point of view. For instance, let's consider a localized vacancy. A localized vacancy, then, the symmetry is completely different. The symmetry is now reduced to reflections and rotation, like somehow what a chemist will learn for the symmetry of a molecule, and the rules after that, the consequences for its NMR spectrum or Raman diffusion spectrum. So you have localized symmetries. And that's why somehow group theory will play a key role in understanding the structure of a defect. But if now you also have associated to the vacancy here, you have some dangling bonds that I show here. And these dangling bonds that you have here will create, by a combination of them, will create, as in a molecule, a state that is localized on the vacancy. Not completely delocalized on the crystal, but now spatially localized on the vacancy. And this will lead, for instance, to discrete energy levels. And if you have, for instance, a semiconductor, or wide bandgap semiconductors, those energy levels can be within the bandgap. And so you can address them like they were like an atom in vacuum. So that's why we would speak somehow of an artificial atom. It's something that we have been able to create through the vacancy due to this effect. Okay? So you see, it's a very different point of view. The first one, in the first one, the standard, we have this delocalized wave function. In the other one, somehow, it's more like a molecular approach. We construct the wave function from the dangling bonds that appear due to the vacancy in the crystals. Okay, and that will be that's what we're going to try to do in the following of the lecture. And to start, let's go to another system, the alkali halide compound. Alkali halide is, for instance, NaCl, rock salt. It's salvine, KCl. All those are ionic crystals, ionic solids that correspond to the electronic bonding between a metallic cation, A+, like Na+, for instance, together due to the difference of electronegativity. The halogenic atoms will take the electron from the metallic atom, and we will have, for instance, Cl-, and then there is the electronic bonding between Na+ and Cl-. And the structure is well known. You certainly have done this as exercise, which was proposed by Madelung. It does not require any quantum mechanics. It's just taking into account that each cation and respectively each anion is surrounded by different anions in the neighborhood. And then you sum all Coulomb interaction between the pair. And then you have this kind of series. And at the end, this kind of series doesn't diverge. and basically sets a minimum to the value. So basically, you have you have here the structure that can appear, and you have that you can determine like that the structure of the crystal. Okay. Now it was found in the 30s by Paul, professor in Göttingen, that if you take those systems, those such crystals, and you induce on them radiation damage. Radiation damage can come, for instance, by electron beam that people had already. So basically, the idea was people developed a powerful electron beam machine, and basically you put a crystal of such halide crystal in the system, and then what was observed, it was that to change completely the color. So for instance, irradiation on an NaCl crystal produced a yellow color. On a KCl crystal, this pink color, and KBr crystal, a green color. And that's why it was, the idea was that something had happened in the crystal. We didn't know, they didn't know at that time what it was, but they suspected that it was centers. And they gave, because somehow the line was quite, was not very broad, the absorption. So they say that it's atomic-like already at that time, and that's what they say it was center, and they gave the name of Farbencenter. Zentrum means center in German, and Farben, it's the color. So that's the reason of the name color center, giving color to the crystals. And they say, okay, to understand that, of course, you need to do some experiments. And they were able, for instance, to do this beautiful experiment where we take these crystals, for instance, and here it is, and then you apply a huge potential difference on two sides. And what they say, that they could accumulate the color on one side, which is a positive electrode. So somehow it leaves, the color is due to electrons trapped in the crystals, and those electrons can, of course, migrate due to the potential difference that is applied on the crystal. So we now have to understand how the system can trap electrons. And basically, again, this comes from vacancy. The radiation damage will create vacancy in the crystal. But now those crystals, so it means, for instance, that you will have a vacancy on an anionic site, Cl-. But again, what you can be, if there is no chloride atom, then the electron coming from the nitrogen atom, in the case of rock salt, will be trapped by the other system, somehow will remain there. Because somehow all around there are positive charge around him, okay, due to the Na plus ions. So somehow a vacancy on an anionic site, can trap a single electron to ensure the overall electrostatic neutrality. So somehow you have a system where you have an electron here confined by the surrounding cation, the surrounding, for instance, nitrogen atoms, at the corner of an octahedron. And what you've built like that with this structure, with this system, is a kind of 3D quantum well. You have an electron trapped within a system that has typical dimension of a few angstrom. Okay? So that was somehow the first realization of a quantum dot using this structure. And basically, there was a law that appeared. If you look to all kind of those crystals that you can produce here in this system, basically, depending on the lattice spacing that you have here, that's the lattice spacing in angstrom, you see that the confinement, which is modified, will lead, as we know from quantum mechanics, will lead to different energy difference in the level of the electron in the box. Okay? And so that's why when the absorption wavelengths gets to smaller here, or to the energy is increased when we have the spacing of the lattice increase. Just because within the electronic level of the electron trap in this box of dimension A, of course, if you reduce the dimension A, the electron difference, the energy difference between the energy level will be increased, and it's exactly that kind of structure that you see. Now, does it work quantitatively? Okay, let me know. We can do it now. We can do it now if you want, and then we continue.